Hello, my name is Ayman Alkhairy, and today I'm going to talk about Class AB power amplifiers, and specifically BJT power amplifiers. But first, I want to give a short introduction about power amplifiers in general, then go through the process of describing the operation of Class AB. Now, what's an amplifier's task? An amplifier is used to increase the power level of an AC input signal by transferring power from a DC power supply to this AC input signal, thus increasing its power level, as we can see here. Now, this can be used for devices that can't detect the power level here, but this amplification would help it detect it, such as on the receiver sides and transmitter sides to improve and increase the power of the signal. Now, we're going to talk about amplifier classes. Now, amplifiers are described or classified based on the portion of the input cycle during which the active device conducts currents. So this is defined as the conduction angle. For example, a Class A power amplifier has a conduction angle of 360 degrees. This means that its active devices are operating all the time, thus having a 360 degrees conduction angle. Now, this is considered bad since the power efficiency would be low since power dissipation is high, uh, since this active device is always operating. Now, for a Class B power amplifier, we have a conduction angle of 180 degrees, which means that an active device or one of the active devices is operating for half an input cycle. Thus, this would have much less power dissipation, meaning much better power efficiency than Class A. Now, Class AB is in between Class A and B. It has a conduction angle that's higher than 180, but also it's much less than 360 degrees. And we're gonna see how this affects the efficiency. Now, first, how a Class A power amplifier works. First, I'll be describing how each component in this circuit operates. But basically, we can see here a transistor in the common emitter configuration. Why? It's because the input is at the base, and the output is at the collector. Thus, the common between is the emitter. Now, why do we have a capacitor here? This capacitor is used for DC blocking. Any input signal will be removed of its DC component, and only an AC signal will pass through this capacitor. Now, what are these resistors for? These resistors are used for voltage biasing, since we need the correct amount for specific amount for voltage to be at this node for this device to operate at the active region, which is about 0.7 volts. And these resistors are used to achieve that. These resistors are also used, the RL and RE used for voltage biasing for the collector and emitter, and they also go in the equation of the voltage gain, since the voltage gain of this is about minus RL over RE, but this capacitor is used to bypass the value of the RE, thus increasing the gain, since it would act as a short circuit for AC input. Thus, this RE won't affect the voltage gain value. So the gain would be higher. Now, this is the Class A operation. Now, why did we design? But first, I want to go back to Class A. The power efficiency for the maximum power efficiency for a Class A power amplifier with a resistive load is about 25%. Now, this is considered bad since we mentioned before that this transistor never shuts down even when we don't have an input signal. Since we're connected to VCC, this transistor will always be passing current, and the power dissipation would be high. So power efficiency is really low, but the output linearity is really good. The output looks exactly the same as the input. So this is the good side of a class A power amplifier. Now, why would we design a class B power amplifier? This is a schematic, a circuit showing a class B power amplifier. We can see here that there's an input at the base and the output at the emitter. So these are configurations of common collectors. And we can see here that this is an NPN transistor and this is a PNP transistor. So for this transistor to work, it needs at least zero point 0.7 volts, about 0.7 volts at the input for it to reach the active region and conduct current. And for this transistor to work, it needs about minus zero point 0.7 volts for it to activate. So this will make us have a good conduction angle, which is, as mentioned before, 180 degrees. But at the same time, if we have an input signal between zero point 0.7 volts and minus zero point 0.7 volts, both transistors would be off and our output would be zero. So this means that any input signal between these levels will output us a 0 volt. This is a bad thing, which means it will deform our signal, our input signal. It will change it. This is called crossover distortion, which I'll describe in the next slide. But as you can see here, since we have a small conduction angle of 180 degrees, power efficiency would be high, which is calculated about a maximum power efficiency would be about 78%, much higher than the class A. But what's crossover distortion? We can see here that, as mentioned before, zero point 0.7 volts to minus zero point 0.7 volts, where both transistors are off, we would have an output of zero. So our signal didn't actually look like this. It was a regular sinusoidal, but from this effect, it became zero in these voltage levels. Thus, this is considered bad, and the quality of the signal would be distorted. Now, to fix the whole process of the crossover distortion, here comes the task of the class AB power amplifier. Now, you can see the circuit here is almost similar to the class B power amplifier, but we have the addition of these two batteries. Now, this is one of the initial configurations, and I'll tell you why in the next slides. But what can we see here is that these batteries are used to push the voltage level at the base at a level it's called an edge of connection. It means that it only needs a small input signal for this transistor to work, or this transistor to reach the active region. So let's take this transistor, for example. If we add a small input, positive input signal, it would add up with the battery value and allow this transistor to operate much earlier than in the case of the class B. Because in class B, it needed to move from 0 volts to 0.7 volts. And this takes time and makes the signal distorted. So with this solution, we improved the crossover distortion by much. It is not identically completely removed, but it's enhanced much better compared to class B. But this configuration is considered very ineffective. Why? It's because we have 1, 2, 3, 4 batteries. So this is very ineffective and costly. Thus, an iteration that improved on this class AB design was this. We used one battery, which is a VCC, and we used these voltage biasing resistors to have the proper amount of voltage at the base nodes of these transistors, which is about 0.7 volts. So these transistors are much cheaper when compared to batteries. So we fixed this solution, but this is not the best solution, since the resistor values change with temperature. And this is unwanted, since if the resistor value is changed due to an effect of temperature, the amount of current passing through these transistors would change. Thus, the output would change also. So this is an unwanted change, and this will cause the signal to slightly differ from the input signal. Now, a way to fix this operation is by replacing these resistors with diodes, as we can see here. Now, these diodes will act the same as the resistor. They will use to bias voltage, since the voltage drop on the diode is about zero point 0.7 volts. So they operate the same as the resistor in this case, but since the diodes are made from the same material that these transistors are made of, the change in temperature would occur and would affect these all these components in the same way. Thus, you could say that the temperature change effect is neglected, and the output won't change as much than in the case of the resistors. So, in this case, we solved this solution of amount of voltage at the base change by adding these diodes. Now, for this configuration, we want to calculate the efficiency. So this is a short example. We have VCC of 5 volts, we have V input of 1 volt, we have R load of 8 ohms, and we want to find the efficiency, which is eta. Now, why did I have RL as 8? Now, most audio devices actually have a load value of about 8 ohms. That's why I use this value. Now, we need to calculate, let me get the pen here. We need to calculate the power efficiency. Now, the rule says, the formula says that power efficiency eta will equal to power at the load, RMS value, over the power at the source times 100%. Now, let's calculate the power at the source value since it's easier. Power at the source equals VCC times IC. Now, we already have the value of the VCC, which is 5, but we need to find IC. Now, IC equals V peak over RL. We know RL as 8 ohms, but we need to find V peak. Now, in this case, as mentioned before, these are common collector transistors. What that means is that their voltage gain is 1. But how do they amplify? They amplify the current gain. The current gain for this circuit is very high, thus allowing very high current to pass at the output. So the power gain would be high, but the voltage gain is the same. So as mentioned in the example, we have an input signal of 1 volts, and the voltage in this node is basically 1 volts plus 0.7 volts. So in this node would be 1.7 volts. And since the voltage gain is equal to 1, the voltage at the output would equal the same voltage at the base here, which would be 1.7 volts also. So this is the V peak for our example. So let's sub this in the IC formula, which would be 1.7 volts over 8 ohms. And another thing is, for this circuit, the class AB, we need to divide the current over pi. Why is that? Now, what we said before that the conduction angle for these transistors is higher than 180 degrees, but it's less than 360 degrees. So let's approximate this value to about pi, which is 180, since we need to find the absolute theoretical maximum power efficiency. So we sub pi. So this would be P source equals VCC times, which is 5, times this value, which would be 0.212 over pi, which equal to 0.338 watts. This is amps. So this is the power at the source. Now we need to find the power at the load, RMS. Now the power at the load equals V out times I at the output. And what's I? I output equals V output over R load. So to combine this equation, it would be V output squared over R load. And since it's an RMS value, we divide by V output squared by square root of 2. So it would be equal to, or square root of 2, all squared over RL. So let's move to the next slide here. So our power at the load would be, as mentioned before, V peak was 1.7 volts at the output over square root of 2, all squared over 8 ohms, which in this case will equals to 0.1806 watts. Now to find eta, the power efficiency, will equal now to 0.1806, which is power at the load, over 0.338 times 100%, which will equal, in our example, about 53.4%. Now, as we can see here, this value is much better than the class A maximum power efficiency value, which was 25%, but at the same time, worse than the class B power amplifier, which was 78%. Now, what are the applications for a class AB power amplifier? Power amplifiers are commonly used in speakers and audio amplifiers, since these devices combine good linear, almost linear output to also having a decent value of power efficiency. And it's basically between class A and B. So it has enough good quality to be used in large speakers, and also a reasonable power efficiency value. Now this was my presentation, and I thank you for watching.